Hey guys, welcome back to another video. In today's video, I'm going to be going over the Lagrange Error Bound. So let's begin. The Lagrange Error Bound, also known as Taylor's Theorem, measures the amount of error between the Taylor polynomial of nth degree and the actual function at some value x. So right here, you can see the formula or equation for the Lagrange Error Bound. Essentially, it says that the remainder at some value x is less than or equal to the nth plus first derivative at some value z, where z is in between the interval between x and c. So imagine you have your center and you have your x over here, for example. Your z will be over here, and it'll just give you the largest value for the nth plus first derivative of x, multiplied by x minus c to the power of n plus 1, divided by n plus 1 factorial. And this is all going to be within an absolute value. This equation closely resembles the Taylor series, or the nth term of a Taylor polynomial, where it's the nth derivative at x multiplied by x minus c, where c is our center of the Taylor polynomial, raised to the power of n, divided by n factorial. So basically, the Lagrange error bound just takes the term right after. So f plus first term. And now let's do some example problems of the Lagrange error bound. So here it is asking us, what is the smallest n possible to approximate e squared for the function f of x is equal to e to the power of x starting at 0 with an error bound less than 0.001. So here we want a remainder or error to be less than or equal to 0.01, and our function or f of x is equal to e to the power of x. So now let's rewrite this including the error bound. So we have f of n plus 1, z, x minus c, but c is 0 because the center is at 0, so we can just keep it as x, then we raise it to n plus 1, and then we divide by the n plus 1 factorial, and we have to make sure that this is less than or equal to 0.01. So now the next thing we need to do is figure out what the nth plus first derivative at z is. So before we do that, we need to know what the nth derivative of x is. So the nth derivative of x, where f of x is e to the power of x, is e to the power of x, because the derivative of e to the power of x is itself. So we just take the next derivative, we get e to the power of x. So now we must find a value z where the remainder becomes the largest, because we want to make sure that our n satisfies the error in such a way that it reduced as much as possible. So our z exists between the interval 2 and 0, because our c is at 0 and our x is at 2. So in some interval here, this interval is closed, by the way, you're going to have the largest value for the nth plus first derivative. So it can be quickly determined that e squared is the largest value, as it is bigger than e to the power of 0 and everything that comes before it. So now we can rewrite the error bound to include e squared. So now we have e squared multiplied by x to the power of n plus 1. And here our x is 2, because we're looking at e squared. So we're plugging in 2 for e to the power of x. So we can put in e squared multiplied by 2 to the power of n plus 1 divided by n plus 1 factorial, and it is less than or equal to 0.01. So now I'm going to move to Desmos. Okay, so now we have Desmos open, and we want to make sure that the error bound is less than 0.01. So this is the Lagrange error bound that we got in the previous step, and what we're going to do here is subtract 0.01 from it, so that whenever this becomes negative, we know that this first part is smaller than 0.01. And I'm just going to keep on plugging in n values until that happens. So we see that n equals 1 does not satisfy it, as it is bigger than 0. N equals 2 does not satisfy it as well. N equals 3 as well. N equals 4 does the same. So when we plug in n equals 10 into the equation, we finally get a negative value, showing us that when n equals 10, the error bound between f of 2 and the polynomial at 2 is less than 0.001. So basically, the Maclaurin series has to have a degree of 10 so that the error bound between the actual function and the polynomial is less than 0.01. Okay, so here we are asked to find what is the smallest n possible, or degree, to approximate the natural log of 2 for the natural log of 1 plus x centered at x equals 0 with an error less than 0.001. So we have that the remainder at x is less than or equal to the f plus first derivative at z multiplied by x minus c, but c is equal to 0 because the center is at 0. So you just have x raised to the power of n plus 1 divided by n plus 1 factorial, and then put it in between absolute value signs, and this is going to be less than 0.001. And when we plug in our x to get the natural log of 2, we just have x equal to 1, because 1 plus 1 is equal to 2. And now we have that the remainder at 1 is less than or equal to the f plus first derivative at z, where z is in between 0 and 1, multiplied by 1. So we can disregard that because anything multiplied by 1 is itself. Then we have n plus 1 factorial. Absolute value is less than 0.01. So now we have to find the n plus first derivative of the function. We know that f of x is equal to the natural log of 1 plus x, and that the first derivative is equal to 1 over 1 plus x, or 1 plus x to the power of negative 1, and that the second derivative by the power rule is negative 1 plus x minus 2, and the third derivative is 2 multiplied by 1 plus x to the power of negative 3, and so on. But what you can start to see here is that there's some sort of factorial property. So you can say that the n plus first derivative of x is going to be negative 1 to the power of n, because we know that the signs alternate, multiplied by n factorial because of the power rule, divided by 1 plus x to the power of n plus 1, because when we have a negative exponent, it's the same thing as saying that you're dividing by this raised to that same exponent, but positive. So now we know that the f derivative is negative 1 to the power of n multiplied by n factorial 1 plus x to the power of n plus 1. And now we must find what value of z makes it the largest possible. Since we have the absolute value, we can disregard the negative 1 part. So we must just find n factorial divided by 1 plus x n to the power 1. What possible value can make this the largest from 0 to 1? Well, if we plug in 0, we get n factorial on its own. But if we were to plug in 1, we would get n factorial divided by 2n plus 1, which is a lot larger than just 1. So we're going to plug in just 1, because if our denominator was larger, our overall error would be smaller, meaning that our n would be less accurate. So now let's plug that into the equation again. We have n factorial multiplied by nothing, is just 1, divided by n plus 1 factorial is less than or equal to 0.01. So n factorial divided by n plus 1 factorial is the same thing as n plus 1 multiplied by n factorial. These cancel out. You have 1 over n plus 1 is less than or equal to 0.001. And now let's go back into decimals to see what value that is. What value of n makes it so that the error is less than 0.001. Here you can see that when we have n equals 1, our error bound is 0.499 away. So that is not enough, because in order for our error to be smaller than 0.01, this whole equation must be less than 0, because it shows that this term is less than this term. So let's plug in n equals 2. After a lot of trial and error, it can be determined that the degree of the Maclaurin polynomial must be greater than or equal to 999 so that the error bound is less than 0.001. So our remainder will be, let's say, 999 at 1 is equal to 0.001. But if you want to be less than 0.01, you can put R, or like the 1000th degree remainder is less than 0.001. Now for our final problem, we have what is the smallest n possible to approximate sine 0.4 for sine x centered at x equals 0 with an error less than 0.001. So applying the same things we did before, our x here is going to be 0.4, and that's going to be less than or equal to the absolute value of f of n plus 1 at z multiplied by x minus c. C is 0, so we don't need the c. So, and that's all raised to the power of n plus 1 divided by n plus 1 factorial, and that is going to be less than or equal to 0.001. So here we have r of n is 0.4 is less than or equal to. Here we replace x with 0.4 n plus 1 over n plus 1 factorial. So now we must find the f plus first derivative at z. So we have our original function of sine of x, and the derivative of sine of x is cosine x, the derivative of cosine x is negative sine x, and the derivative of negative sine x is negative cosine x, and so on. So it's just going to keep on alternating signs. So we know that the trigonometric functions sine and cosine range from -1 to 1. So from the interval 0 to 0.4, we want to find the z value so that the f plus first derivative is the largest. We don't know what the f plus first derivative is. It could be either cosine or sine. So we must choose the largest value. I mean, both of these functions that they have in common. So the largest value that they both share is 1. So this term right here, or component of the Lagrange error bound, can be replaced with 1 because that is the largest possible value for either sine and cosine x. Then we just multiply by 0.4 to the power of n plus 1 divided by n plus 1 factorial, and this is less than or equal to 0.01. And now let's go back into Desmos to see what value of n makes it less than 0.001. So here we have the equation determined in the last part, and we have the error that we want to become less than, and we have our n here. We're going to keep on plugging in values until our error is less than 0, or the difference is less than 0. So we can see that when n equals 4, the error bound between the actual function and the polynomial is less than 0.001 at the degree 4. So we have determined that the remainder of 4th degree Maclaurin polynomial at 0.4 has an error less than 0.01 for sine of x. Thank you for watching today's video. I hope you enjoyed, and stay tuned for more.